Welcome. This is the regression analysis course. My name is Nicota Serbat. I'm an associate professor in School of Industrial and System Engineering. The topic of this lesson is inference for regression parameters under multiple linear regression. What we learn in this lesson is how the statistical properties of the estimated regression coefficients, along with procedures on how to estimate confidence intervals and perform hypothesis testing for the regression coefficients. Let's begin first with the properties of the regression estimators. Just like in simple linear regression, the expected values of the estimators are equal to the true parameters. The variance of the estimated regression coefficients is on a slide. Is sigma squared times the inverse matrix of x transpose times x. Recall that x is the design matrix. So what we see here is that the variance of beta hat is now a variance. I remind you that beta hat is a vector of estimated regression coefficients. If we have 10 predictors, the vector will have a length of 11. So because this is a vector, now the variance is going to be a matrix. On a diagonal, we'll include the variances of the coefficients, and off the diagonal will be the covariances between the estimated regression coefficients. Furthermore, beta hat is a linear combination of the y's. And if we assume normality, that means the error terms are normal, or the response variable are normally distributed, then beta hat is also distributed as a normal distribution, with beta as the mean and sigma as the covariance matrix. What point to make here is that the estimator beta hat is unbiased for beta, because the expectation of the estimator is equal to the true parameter. Also, the sampling distribution of beta hat is normal, but it depends, the covariance matrix depends on sigma square. And we do not know sigma square. So what should we do? We're going to replace sigma square with a mean square error, the estimated variance I presented in one of the previous lessons, which is equal to the sum of squared of residuals divided by n minus p minus 1. And also I discussed then that the sampling distribution is a chi-square distribution with n minus p minus 1 degrees of freedom. So now when we replace sigma square with its estimator, the sampling distribution for beta hat, for individual beta hats, are going to be a t distribution with n minus p minus 1 degrees of freedom, where n minus p minus 1 comes from the degrees of freedom of the variance estimator. Now we can derive confidence intervals for beta j using the assumption, the t sampling distribution. So this will be how the confidence interval will look like. The way we use this confidence interval is if we can answer questions whether beta j is statistically significant. That means we check whether 0 is in a confidence interval. And if it's not, we conclude that beta j is statistically significant. But why is this a t interval? Remember, the sampling distribution for the individual regression coefficients is a t distribution with n minus p minus 1 degrees of freedom. So if I want to build a 1 minus alpha confidence interval, now I center it at the estimate of beta j, which is beta hat j, plus or minus the t critical point. Again, I'm using here n minus p minus 1 because the sampling distribution is t n minus p minus 1 times the standard deviation. In terms of statistical inference based on hypothesis testing, we can use it, for example, for testing for statistical significance of individual beta j. And we can use, again, the t-test. Here, the null hypothesis is whether the coefficient is 0 versus is not equal to 0. The t-value is very similar to what we use under a simple linear regression, is the estimator minus 0 divided by the standard error. If this t-value is large, we reject the null hypothesis, and thus we conclude that the coefficient is statistically significant. How will procedure change if we test whether the coefficient is equal to a constant versus is not? Again, the t-value looks very similar, but we're going to replace 0 with the null value b. And we want to, we test, we reject if the t-value is larger than t alpha over 2n minus p minus 1 when the absolute value of t-value, if the t-value is larger than the critical point. Alternatively, we can compute the p-value as 2 times the probability that t-distribution with n minus p minus 1 is greater than the absolute value of the t-value. Again, this is absolute value of the t-value. If the p-value is small, then that means, for example, if the p-value is more than 0.01, we conclude that we reject the null hypothesis. We reject the null hypothesis that beta 0 is equal to 0. How would the procedure change if we test whether the coefficient is statistically positive or statistically negative? If we want to test for positive relationship, then the p-value is the probability of the t-distribution with n minus p minus 1 greater than t-value. So we're not using the absolute value, and we're not using the 2 in front. If we want to test the negative relationship, the p-value is the probability of the left tail of the t-distribution, so it's when it's smaller than the t-value. And this is not going to be an absolute value, and we don't have the 2 times the probability anymore. In this lesson, we learn about the statistical properties of the regression coefficients, along with procedures for estimating confidence intervals and performing hypothesis testing for individual regression coefficients. Thank you.